polynomial h of z, which is given here, has a 0 of 3 minus I. We want to determine the value of a and all of the other zeros of h of z. Now the important thing is here that when we know that we have a complex root and that all of the coefficients are real, then the conjugate must also be a root. And that means that z minus 3 minus I is a factor, and so is z minus 3 plus I. Now let's expand this out. We'll get z squared, take away 3 minus I plus 3 plus I z plus 3 minus I, 3 plus I. So that gives us z squared minus 6z. Remember, this is a difference of two squares, so it's going to be 3 squared plus 1, so plus 10. So we now know that z to the 4 minus 6z cubed plus 3az squared minus 30z plus 10a is equal to z squared minus 6z plus 10, and then the other factor must also be quadratic. Z squared, let's say that's bz's, and this is 10, this is a, so that must be plus a on the end here. So that gives us a constant term of 10a. So let's look perhaps at the z cubed term. So on the left we've got minus 6z cubed. On the right we'll get a z cubed from here, and we'll get one from here. So that's minus 6z cubed plus bz cubed, and that must mean that b is equal to 0. So now we know that this is z squared plus a. So let's look perhaps at the z term. So where are we going to get those from when we have z squared minus 6z plus 10 z squared plus a? So we know this is minus 30z. What's that going to be equal to? So what will give us a z here? Well, the only one that can give us a z is this one. So that's going to be minus 6a z. And that tells me straight away that a is equal to 5. So in other words, we have z squared plus 5. So if we want the other zeros, that would give us that z is equal to plus or minus root 5 I.